In this question we are being asked, and we are given that fish enter a lake at a rate modeled by function e, and e for enter given by this expression here, and then fish leave the lake at another function L given by this function here, and L for leave. Both of these functions are measured in fish per hour, and time is measured in hours since midnight, so since time equals 0. And then the first question is, how many fish enters the lake over the 5-hour period between midnight and 5 a.m.? And we need to calculate the answer as well. So let's write this. This is actually an integral from 0 to 5 of the function of the rate function at which the fish enters the lake. So it's 20 plus 15 sine pi t over 6 dt. And so we use a calculator to calculate this number. So here we need to calculate the integral from 0 to 5, and so let's do the integral from 0 to 5 of the function e of t. So function e of t is 20 plus 15 times sine of pi, which is second pi, x, doesn't matter whether x or t, divided by 6, close parentheses, and that is dx. So enter, and so our answer is between time 0 and 5, 153 fish will enter the lake. So 153 fish. In this part of the question we are being asked what is the average number of fish, average, not total, that leave the lake over this period, 5-hour period, from 0 to 5 a.m. And so again, the total number of fish that leave the lake will be given by this expression 0 to 5 L of t dt. That's the total number of fish. And then the average we just need to divide by 5 minus 0, which is equal to 1 over 5 times integral 0 to 5 of the function L, 4 plus 2 to the power 0.1 t squared dt. And so we need to use the calculator to calculate this as well. So here we need to take the integral again from 0 to 5, integral from 0 to 5 of the function L, and then not forget to divide by 5 because we are asked to do the average rather than calculate the average rather than the total. So function L is 4 plus 2 to the power 0.1 times x squared, and then dx, and then we need, as I said, divide by 5. So this is the average number of fish leaving the lake between the time 0 and 5, about 6 fish. In this part of the question we are being asked at what time t between 0 and 8 the number of fish in the lake is the greatest, and we need to justify our answer. So let's look at the rate of change of the number of fish in the lake, and so this will be e of t minus L of t. So this is the rate at which the fish enters the lake, and this is the rate at which it leaves the lake. And so at a maximum or a minimum, this should be 0, because these are continuous functions. And so we need to find t such that this is the case, and then look at their maximum and minimum there. In this case, we need to find t such that the rate of change, e of t minus L of t, is equal to 0, and then check which of those t's gives the maximum value for the number of fish in the lake. So let's use this plotting. Let's write the function itself and find 0. So e of t is 20 plus 15 times sine of pi x divided by 6, close parentheses, minus 4 minus 2 to the power 0.1 times x squared. So this is our function. Let's check what window we have. Window is between 0 and 8 as we needed. And the minimum and maximum are what they are. Let's see what the graph will show us. So this function is continuous, remember that, and so we can see that initially the number of fish increases because this is the rate of change, and it increases all the way up until this point, and then it starts to decrease. So really we have a maximum at this point because this is smaller, the amount of fish here is smaller, and the amount of fish at the endpoints t equals 0 and t equals 8 is different, is lower than at this point. So let's find what this point is. So let's go back to window. It's between, I would say, 6, maybe 1 and 6.3. So let's do 6.1 here, and then let's do 6.3 here. And if you made a mistake here, you can just always change these limits a little bit. You'll see what I mean just in a second. Let's do 0.1, so it's in between these two. It will have this dash bit at a point 6.2, and then the range here. Let's probably decrease this a little bit to -5 and 5. Okay, let's do the graphing. And so we can see that the answer is about 6.2. But in order for us to get exact, a more precise point, let's do trace. And so y is positive, we move to the right. Y is still slightly positive, we move a little bit further, so y is negative. So it's between the point 6.202 thousandths and 6.204 thousandths. So let's say it's 6.203. That's our answer, and as we showed, this is the maximum. So here we are being asked whether the rate of change in the number of fish is decreasing or increasing at a time t equals 5. And so to find that, we need to calculate the derivative of e of t minus L of t, the derivative with respect to t, and evaluate that at a t equals 5. So let's do that numerically. So here we also need to take derivative of the rate of change function and evaluate it at a point t equals 5. So let's do it numerically here. And so function is derivative with respect to x, doesn't matter, so the function e of t is 20 plus 15 times sine of pi x divided by 6, close parentheses, minus 4 minus 2 to the power 0.1 times x squared, and this is at the 0.5. And note here that we don't actually need to take the derivative because calculator will do it for us and evaluate it at x equals 5. So let's do enter. And so we see that the rate of change is decreasing at a point at t equals 5. So the number of fish decreases in the lake. The rate of change decreases